scalings. Now notice where the number is in there. Okay, horizontal scalings are the worst. They are the most confusing. That's the bad news. The good news is we're not going to do very many of them. Like most of the time you don't need to really worry about them, but they will come up once in a while and I'll remind you. They're weird. I think the main time we're going to see horizontal scalings is in trig, when we take our sine and cosine graphs and we change like the period and squish them this way or that way. I don't know if you remember doing that a little bit in second grade. That's the idea. Okay, so the weird thing is instead of it doubling the x value, it's actually going to have the opposite effect. It's going to half the x value. I know, horizontals are whack. Okay, so half of 0 is still 0. So this is going to be half of the x value. So then half of 2 is 1, half of 4 is 2, half of 5 is 2.5. Again, if you don't believe me, instead of me taking time for us to explore that right now, feel free to use a graphic calculator or Desmos and just explore it with functions. Use an equation and practice like just changing, like putting a number in with the x value in the parentheses and see how it changes. Maybe we'll do that another time. Okay, so in point at 0, 1, and we have a point at 1, 3, and we have a point at 2, 3. And we have a point at 2.55. Now, here is a good illustration for why I don't really like to use the words skinny and wide when I refer to the graph. I prefer to use the words stretch and compress because this one now looks skinny. But is it the same as the other one we did earlier that looked skinny? They're both skinnier than what they appear to be skinnier than the original, but in fact, this one is skinnier than the original. The other one was just stretched this way and had the appearance of being skinny. They're kind of both similar to each other, but this one's smaller than the one we did earlier. I think we talked about it this ahead. Notice how this one is twice as tall as this one, but the same width. This one is the same height, but half the width, and those two pictures are both similar to each other, same shape, different sizes. So it's kind of interesting how changing that scale factor on the horizontal value affects that. Okay, let's go ahead and do this one right here. Use the graph of f of x to sketch the graph of g of x equals 2x plus 1. And then we're going to state domain and range. It's really not as bad as it looks. Maybe we're actually going to plug in some points, so we'll actually see this in action. This will give us a chance to actually see that it's actually going this direction. I guess I should have explained that. So this is going to be, this one was a horizontal compression, wasn't it? So in order for us to have a stretch, we would have a fraction. All right, just adding that note on there. All right, let's go ahead and graph our same graph, same points. Okay. You guys know how to make T-charts, right? Everyone talk about when I see a T-chart. They might become your best friend in this class. the same x values we have here, just for fun. See how they work out. So I'm going to plug in a 0. So 2 times 0 plus 1. So let's see if that agrees with the stuff we've been learning today. So we know we have like a not vertical, we have a horizontal compression, and we have a shift. Where is that shift? That's not on the outside, that's on the inside. Interesting. So what's the shift actually going to look like? Well, let's just keep going. The numbers might get ugly. Okay, plug in 1 just for fun. So 2 times 1 plus 1. So I plugged in a 1, but now I have the square root of 3. Weird. All right, let's try 4. I think 4 is going to be better. 4 times 2 plus 1. Square root of 9. That one is nice. Is there anything else we can plug in that's going to make this give us a pretty answer? Like, no, I'm trying to think, because right now we have the square, so if we had 16, we could do like 7.5. Not kind of ugly, but not too bad. 7.5, 2 times 7.5 is 15, plus 1 is 16, and the square root of 16 is 4. Okay. So I have a point at 0, 1. So right now I'm just using a t-chart to kind of analyze the numbers, and then we're going to compare them and figure out what happens. And I'll show you a trick to help you understand a little bit. So 1 squared is 3. I don't remember. Square root of 3 is approximately 1.4. Square root of 3 approximately. I'm trying to remember. Does that sound about right? Has anyone tried it lately? Square root of 4 is 2, so maybe it's higher than that. Maybe it's 1.7. 1.7. Okay, thank you. I was mixing up my square root of 2 and my square root of 3, which are going to be important in the trick. Okay, 4.7, so over 1 up 4.7, and then over 4, 3, and then over 7.5 up 4. Weird. What exactly happens? Well, I'm going to take my actual function here really fast. Square root of 2x plus 1. The first thing that's easier to understand is if we take out that 2. We actually want to take the 2 out of this inside part like this, because then that will give us the appropriate shift amount. How much is this actually shifted in what direction? Based on this number right here. That would be a shift left 1/2. Sound weird? We do have some half stuff going on, right? Okay, so then what should that 2 be doing? Let me show you another little tricky thing you can do if the compressing horizontally stuff is messing with your brain. You can actually take that out. So we have a square root of 2 in front of our square root of x plus 1/2. That changes this to a 1.4 there. I think I have the right decimal this time. So instead of thinking of this as a horizontal compression, we can now think of this as a vertical stretch of 1.4. So a vertical compression of 2, a horizontal compression of 2 is the same as a vertical stretch of square root of 2. Are you becoming a little confused with mind blown at the moment? I feel like that's normal. It's okay. Don't stress too much. Does it make sense that a horizontal compression and a vertical stretch are going to have the same appearance on the graph? Pushing it this way and stretching it that way are going to give it that same type of effect, right? Okay, we'll explore those more as needed. I wouldn't stress too much. Okay, now we just have some other things to practice various things together. So I want you to give this a try. We'll be using the same square root function over and over. I want you to go ahead and take what you've learned today and apply it. We can even talk through it first. What's the plus 3 going to do to our left? Remembering everything left, nothing to the right. What is the minus 2 going to do? Yep. Okay, so here's what I want you to work on right now for me, is to figure out where the points are going to be. So the points we've been using for this graph, we plugged in 0, we got 0, we plugged in 1, we got 1, we plugged in 4, we got 2, we plugged in 9, we got 3. So find the corresponding points for me after you do this. Okay, work on that right now. Still don't see any questions.